Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about three nonlinear recurrences. Since we just finished up showing that we could solve any linear recurrence, let's look at a couple nonlinear ones to see what we can do with them. The first one is a fun game called the Towers of Hanoi. And this involves n disks stacked on the first of three pegs on a board. You're allowed to move one peg to another as long as the disks on each peg are decreasing in size from bottom to top. So a smaller peg can rest on a larger peg, but you can't put a larger peg on top of a smaller peg. So you see the yellow one is the widest here, and then the blue is middle, and the red is smallest. So h sub n is the number of moves to get all the disks onto the second peg, but you're only allowed to move one disk at a time. So how can we even do this, and what's the minimum number of moves? Well, here's one thing we could do. We can move the red disk to the next peg, and then we can move the blue disk to the third peg, and now that we have that there, we can move the red disk onto either the yellow or the blue peg. Let's move it onto the blue. Now we can move the yellow disk, and that's really good because we want to start stacking them on the second peg. Now we have to get this blue and red stack back on top here, so let's move the red, and then we're free to move the blue onto the yellow, and finally we can put the red on top. And we win! So if you counted carefully, that was 7 moves, and we want to know how many moves in general if there are n disks. Here there was 3 disks, but how about if there's 4? Well, let's look at the case of 4 disks. We can use what we did for 3 disks to move the top 3 disks to any other peg. Let's say we want to move them to the third peg. It will take 7 moves. And then we can move the yellow disk and then move those back with 7 more moves. So let's try that. I'm going to skip all the 7 moves to get 3 disks over to another peg, plus 1 more move, plus 7 more moves to get these back on top of another peg, and now we're done. So in general, h sub n is going to be equal to h sub n minus 1 plus another h sub n minus 1, or 2h sub n minus 1 plus 1. Let's use this recursion to unwind it a little bit and see if we can guess what the nonlinear recurrence comes out to. Notice it is nonlinear because it's not just a linear combination of previous terms. You have this pesky plus 1 in the way, but it almost looks like a depth 1 linear recurrence, and it's very close to that in explicit formulas too. So h1 is 1, because if you only have one disk, you only need one move to move it to another peg. And so that's our initial condition, and then using this recursion, well, we take twice the previous number plus 1. 3 times 2 plus 1 is our 7 that we found out. 7 times 2 plus 1 is 15 for 4 disks. 15 times 2 plus 1 is 31. 31 times 2 plus 1 is 63, and so on. And these look very close to a familiar sequence. In fact, they're one off from the doubling sequence. So we guess that h of n is 2 to the n minus 1. 2, 4, 8, 16, 32, and 64 are what you get when you add 1 to this sequence, so it is indeed 1 less than 2 to the n minus 1. We can check that this satisfies the recursion by plugging it in, and indeed 2 times 2 to the n minus 1 plus 1, you expand it out and you get a minus 2 plus a 1, and you do get 2 to the n minus 1 in the end. Let's look at another fun nonlinear recursion. Let's let p sub n be the maximum number of regions n lines can divide the plane into. So here's an example of one line dividing the plane into 2 regions. One line always divides the plane into 2 regions. But what if we add another line? Well, if we add the other line parallel to this line, it would divide into 3 regions. But if we have it crossing, then we get 4 regions. 1, 2, 3, 4. So let's see what happens when we add a third line. So again, if it's parallel to 1, you're not going to get as much. You want it to intersect both lines. Also, you don't want it to go through an intersection point. But you can show that you can always make it intersect all the previous lines exactly once. And so if the third line is, say, going through here, then you would split 1, 2, 3 of the regions, and so you would add 3 more regions total to our sum. Here's an example for 4. You see we added 3, and then a 4th line actually splits all 3 of the other lines, and so it adds 4 more regions. And so at each step, we start with p1 equals 2, and p sub n is p sub n minus 1 plus n. You can always add n more regions to the previous step. This is certainly nonlinear because it has an n term. So let's try to solve this recursion. P sub 1 equals 2, and p sub n is p sub n minus 1 plus n. Now if we unwind the recursion, it doesn't look as obvious as what was going on in the Towers of Hanoi problem. That one was basically doubling. But this one is 2, 4, 7, 11, 16, 22. Well, we start at 2 and we add 2, and then we add 3, and then we add 4, and then we add 5, and then we add 6 by the definition of the recursion. So we actually could just write that out and say p sub 6 is 2 plus 2 plus 3 plus 4 plus 5 plus 6, which is almost like 1 plus 2 plus 3 plus 4 plus 5 plus 6. It's just one off of that. And in general, p sub n is going to be 2 plus the sum of the numbers from 2 to n. If we split this 2 into 1 plus 1, then we get 1 plus the sum of the numbers from 1 to n, and that's our triangular number, which by Gauss's formula is n times n plus 1 over 2. So that gives us an explicit formula for p sub n. Let's look at one other nonlinear recursion. Derangements. So d sub n is the number of permutations of 1 through n in which every number moves. You can't have a permutation like 4, 2, 1, 3 because 2 is still in the second position. Nobody's allowed to be in their own position that they are in 1, 2, 3, 4. So here's all the derangements of 1, 2, 3, 4 written out. There are 9 of them. Counting derangements is hard in general. And it's hard to find explicit formulas. So this is an example of where finding the recursive formula is actually the best we can do. And it is nonlinear. There's a couple different recursive formulas, d sub 1 equals 1, d sub 2 equals 1, and d sub n is n minus 1 times d sub n minus 1 plus d sub n minus 2. So it almost looks like a depth 2 linear recurrence, except it has this factor of n minus 1 out front. So that depends on n, it's not a constant, so it's not linear. There's another recursion, you can actually show this is equivalent to d sub n equals n times d sub n minus 1 plus minus 1 to the n. So lots of different recursions for derangements. And the closest thing we have to an explicit formula is that it's the closest integer to n factorial over e. So this is one thing magical that comes out of these formulas actually. You do get factorials, you get e if you expand things out, but there's no real sort of closed formula that doesn't involve some kind of approximation like this. So not every nonlinear recursion has a solution. Not every recursion can be simplified. Just because we had such a clean answer for all the linear recursions doesn't mean we can always solve them. But that's okay. Once we have a recursion, we can at least calculate in an efficient way. So now you try. How does the Towers of Hanoi problem change if you have 4 pegs to work with instead of 3? And that's all for today, and I'll see you next time.